Okay, so today we're going to talk about standardizing a normal random variable, okay? So, Unit 1, we talked about a z-score, okay? So we already know that a z-score compares things that are really not comparable, like an ACT score and an SAT score, okay? It has no label. It's just putting everything on kind of a normal curve. So the following formula can transform any normal random variable into a standard normal random variable, aka, here's how we find the z-score. You take your data value or your normal random variable, you subtract the mean, and you divide by the standard deviation. Okay? So if we look at the individual pieces, exactly how this transformation works becomes clear. Like, why does the z-score work? Why does it make everything comparable? Here's how. First of all, the numerator, which is x minus mu, okay, your random variable minus the mean, centers the z distribution around 0. It takes whatever your data values are. They could be in the hundreds, they could be in the thousands, they could be whatever. If you take that data value and you subtract the mean, it's shifting it and it's centering it around 0. Okay? Then, by subtracting the mean of the random variable from each data value, the mean of the resulting random variable will be 0. Here's what that means. This means nothing unless you see it. So here I have a list of data values, okay? I want you to go ahead and find the mean and the standard deviation, okay? So we're going to say average of all of these values in standard deviation, standard deviation, and I'm going to say this is a population. Oh. You should get about, maybe it's a sample, hold on. Sorry, it's a sample, And let's round it just to the nearest tenth. Okay? Now what we're going to do over here is we're going to find the corresponding z-value for every one of these data values. So to find the z-value, we're just going to use that formula up there. So you're taking the random variable, subtracting the mean, and dividing by the standard deviation. But I don't want to do that every time, so let's create a formula. So we're going to go equals, and what do we have to put around the numerator? Parentheses. So parentheses, and then I'm going to, oh, look at the frowny face. And then I'm going to take the random variable, okay, and subtract the mean, which is down here, we said 10. But what do I need to do to that mean? Why? Yeah, we want to absolute cell reference that. We want the dollar signs. We don't want it to move. We don't want that to change. Then what do? Close your parentheses. And then we're going to divide it by the standard deviation. Do I want the standard deviation to change? No. So again, we need to do an absolute cell reference on that. So it should look like this. And then you're going to hit enter, and you should get negative 1.3. Let's just round it to the nearest tenth again. And watch what I do here. I'm highlighting that whole column, and I'm going to go ahead and make it to the nearest tenth so I don't have to do it every single time. Okay? Highlight it?
Oh, I got it.
Okay. Then, so we don't have to do it every single time, click on the little box, drag it all the way down. Drag it all the way down. Now, here's what's really, really cool, guys. When we learned about the z-score, we learned that it standardizes values, okay? So it shifts it all around 0. But it's hard to understand that unless you really, really see it. So check this out. I found the z-score for each one of these random variables. Let's come down here and find the average, the mean of all of those z-scores. So if I find the average of all of those z-scores, what do you guys get? 0. That's literally the whole point of it. We took each one of your values and we said, let's alter it, let's change it, so that now the mean is no longer 10. We just shifted the mean to 0. We took our average and we shifted it to 0. And here's what each one of those values turned into when we did that. Okay? Now let's check our standard deviation. So standard deviation, and again it's a sample. And we're going to find out of all of that, all of your z-scores. And what do you get? You should get close to 1. Some of you might get 0.9, some of you might get 1.1. There's a little bit of rounding in there, but you should get about 1. And what that's doing is that z-score is taking all of your random variables and turning it into a standard normal distribution. So we can put it on our little graph, and we can have a mean of 0 and a standard deviation of 1. It's standardizing your values. It's saying, okay, I have a mean of 10 and a standard deviation of 6.5. I want to change that to have a mean of 0 and a standard deviation of 1. So your z-score is your new value that represents your original values. So by finding the z-score of each value, you have shifted the location of the data set to 0. Okay? You haven't changed anything. You manipulated it. You shifted it. The interrelationship of the data points to one another has not changed. Okay? So the relationship between 1 and 3 is maintained with their z-score of the relationship between negative 1.4 and negative 1.1. And I understand what you're thinking. You're like, Mrs. Getz, the difference between 1 and 3 is 2, and the difference between negative 1.4 and negative 1.1 is 0.3. That's not what I'm meaning. The relationship between them has not changed. Okay? It's all in reference to their new mean and new standard deviation. Last class we talked about the norm.s.dist and norm.s.inverse functions to use on standard normal distributions that have a mean of 0 and a standard deviation of 1. The dot s in those functions stands for standards, a standard normal distribution. Today we're going to look at problems that have any mean or standard deviation. Instead of just having a mean of 0 and a standard deviation of 1, we're going to give you more real-world applicable problems where they have any mean or any standard deviation. So long as you have the mean and standard deviation, you should be able to find what you're looking for. So how to find the area under any normal distribution in Excel, doesn't have to be standard, is just norm.dist, okay? So the difference between norm.dist and norm.s.dist is the dot s. You only use the dot s if you have a mean of 0 and a standard deviation of 1. If your mean and standard deviation are literally anything else, you just use norm.dist, okay? Now, when you do that, you're going to put in your data value, so your original random value, then your mean, your standard deviation, and again, you're going to put true. Now, the result is always the area to the left of the z-score, just like we learned. So on number 1, it says IQ scores, as on the Welcher test, are normally distributed with a mean of 100 and a standard deviation of 15. What would be the probability that an adult would score less than 90 on the test? So when they tell you that it's normally distributed, what that means is you can draw yourself a normal curve. Okay? IQ scores are normally distributed, but this is where it gets a little different than the last lesson. The last lesson we would always put 0 in the middle. Whatever goes in the middle is your mean. So here they tell me it has a mean of 100, okay, and a standard deviation of 15, okay, a standard deviation of 15. If you would like, you can come in here and you can put, okay, 115, 130, 145, and then count down as well, but you do not have to do that. You are welcome to do that, but it is not required, okay? It does say next, what would be the probability that an adult would score less than 90 on the test? So would that be on the right side or the left side of my mean? Left side. So I'm going to put where 90 is going to be about, okay? And it wants less than 90, so it's going to be shaded this direction. Okay, what would be the probability that an adult would score less than 90 on the test? Since my mean is 100 and my standard deviation is 15, we have to use norm.dist. So I'm going to come over here and click on a cell. And we're going to type in equals norm.dist, and then we put in the values. The x value is what is the question asking. The question is asking score less than 90. So we're going to put 90 in for x, comma. Your mean is given, so that's 100, comma. Your standard deviation is given, it's 15, comma, and then true, okay? Again, whenever you do these formulas, they always give you the area to the left. So on this one, I'm allowed to just put that bad boy in and look at the results that it gives me. That tells me that I'm going to get this number right here, but since we're using Hawks, they usually say to 4 decimal places, so I'm going to change that. So 0.2525, the area to the left of 90 is about 0.2525. That means about 25% would score less than 90 on the test. Are we okay with that? Let's go to number 2. What is the probability that an adult would score more than 105 on the test? So we're using the same information. It's still based on that standard normal curve with my mean of 100. And it wants to know what is the probability that an adult would score more than 105. So 105 is going to be more than my mean, so this is going to be 105. And if they say score more than, would I shade to the right or to the left of that? To the right. Okay? Now here's where things are a little bit tricky. The norm.dist function gives me the area to the left. So what am I going to have to type in to get the area to the right? Very good. 1 minus norm.dist. And then we just put in our information. What's my x value going to be for this one? 105. What's my mean? 100. What's my standard deviation? Still 15. And what do I put, true or false? True. And again, I like 4 decimals. So about 37% would score more than 105 on the test. Okay? Number 3, what's the probability that an adult would score between 79 and 133? Again, it's the same problem. So I'm going to have my standard normal curve. I have my mean of 100. And they say, what's the probability that an adult would score between 79, so that's going to be down here, 79, and 133. That's going to be up here, 133. Now, if you're one of those people that's like, I think 79 might be a little further to the left, it's just a sketch. It's okay if it's not 100% accurate. You're just trying to get a visual to help you understand which formula to use. So I want this information right here. I want to know what's the area between those two values. Do you remember how we got that? We subtract the two. I take the norm.dist of 133, which gives me all of this blue area right there. Are we okay with that? And I subtract the norm.dist of 79, and that gives me the yellow area. So if I take the blue area minus the yellow area, which looks green because now it's overlapping, I'm left with whatever's in the middle. So we're going to have equals norm.dist, and we're going to start with the big one. So 133, 100, 15, and true. Close those parentheses. And then we're going to subtract norm.dist of the smaller one. What's my smaller one here? 79, 100, 15, and true. Now, can you do those in 2 separate cells? Absolutely. If you want to find the norm.dist of the big one and then the norm.dist of the small one and then subtract them, I'm also okay with that. And then, again, I'm going to go to 4 decimal places. So that means 0.9053. The area between 79 and 133, the area between those two scores is 0.9053. That means about 91% of the adults will score between 79 and 133. We okay with that? Okay. Number 4, the weights of a newborn baby boys. Let me say that again because I messed that up. The weights of newborn baby boys born at a local hospital are believed to have a normal distribution with a mean of 3,537 grams and a variance of 285,156. If a newborn baby boy born at the local hospital is randomly selected, find the probability that the weight will be less than 4,172 grams. First thing you should do is always sketch your curve. They tell me it's a normal distribution. That's a highlighter. That's not what I want. They tell me it's a normal distribution, so I know it's going to look like this. What is my mean? What goes in the middle? $35, $37, very good. What's my standard deviation here? Oh, they gave me the variance, so I have to square root it, right? So since we don't need that for the actual problem, I'm just going to hold tight on that, and I'll show you what I do with it in a minute. Now, find the probability that the weight will be less than 4172. Is that going to be to the right or to the left of this mean? To the right, so I find where 4172 should be. And am I shading to the left or to the right? To the left. Awesome. So does that mean I have to do anything special? No, if it's to the left, it's literally just what you see is what you get. But here's where things are a little different, okay? So we're going to type in norm.dist. What am I putting in for my x value? 4172. What about my mean? 35, 37. Now my standard deviation wasn't given to me, but my variance was. And we know that to find the standard deviation, we have to take the square root of the variance, right? I'm going to type it right in there. I'm just going to type in SQRT of, and then type in the number, 285156. And it will figure it out for me. Okay? You don't have to type in equals because it's already, like, we're already in a formula. It understands. So all you have to do is type in square root right in there and then true, and it'll give you the value. Again, you want to make sure that's 4 decimals. Now there's another way that you can do it if that's like, I know some people are like, that's too much going on. No big deal. You can come over here and you can put standard deviation, and you can just figure it out right here, equals square root of 285,156. And then when you're finding this information, you can go equals norm.dist, if I could type today, wow, 4172, comma, 3537. And since this is a nice number, you could actually type it in, 534 if you would like, or you could just do a cell reference if you would like. That will also work. Okay, those are your options. All right. Now, let's talk about the opposite of that. Suppose we are given the probability and we're asked to find the corresponding x value. It's the opposite of what we have been doing. So just like when we did the standard distribution, that was norm.s.dist, and then the opposite of that was norm.s.inverse, the same thing is going to happen here. How to find the x value when the area under a normal distribution is given in Excel is norm.inv, and then you just give the probability, the mean, and the standard deviation. So on number 5, suppose SAT writing scores are normally distributed with a mean of 488 and a standard deviation of 111. So what I'm going to do is I'm going to sketch that. I've got a standard curve. Come on. No, we don't want to draw today. Okay. All right, we're going to have a great day today. Pen is not working. So we're going to have, there we go, a normal curve with a mean of 488 and a standard deviation of 111. Okay? A university plans to award scholarships to students whose scores are in the top 8%. So would the top 8% be on the left side or the right side? The right side. And would it be closer to the mean or further away? Further away, right? Like top 8%, that's going to be like over here, the top 8%. Okay? What is the minimum score required to receive a scholarship? Now this is a little weird because they gave me a percentage. So when they give you a percentage, you have to be smart enough to understand what that is as an area. So what's the area over here if the percentage is 8%? 0.08, okay? Now remember, this formula doesn't use things to the right. It uses things to the left. So if this is 0.8 over here, what is all of this space over here? 0.92. So when you're using this formula, you're going to have to type in norm.inv. And the probability that you have to use is whatever's to the left. So for here, that would be 0.92. The mean would be 488, and the standard deviation is 111. Now, Hawks will tell you how they want you to round. For this practice, I'm just going to round to the nearest whole number. And that means the question was, what is the minimum score required to receive a scholarship? And that's going to be 644. So that means this right here is 644. That's your X value. You have to receive a 644 on the SAT writing score to be in the top 8%. Okay? All right, let's go to number 6. If a normal distribution, so I'm going to sketch that out, has a mean of 28.0 and a standard deviation of 2.5, what is the value of the random variable x that has an area to the right that is equal to 0.067? So I want you to think about this. An area to the right of 0.067, is that a really big number or not? No, that's a really, really small number. What would that be as a percentage? So they're saying the area to the right, there's only 6.7% to the right. So that's going to be over here, and is it going to be closer to the mean or further away? Yeah, it's going to be even further away than the problem we just worked on. So here's what we have. The area to the right is going to be 0.067. They want to know what's the corresponding x value that goes with that. So it's going to be the same concept as what we did on number 5. First, we're going to have to figure out what's the area of this guy over here. You have a couple of ways you can do that. You can just come over here and you can type in, equals 1 minus 0.067, and it'll give it to you. Or you could do that right into your formula. You can come over here and go inverse, INV, yikes. The probability would be 1 minus 0.067. The mean would be 28.0, and the standard deviation is 2.5. So what would that be? And here, if you'll notice, they rounded this guy to the nearest tenth, this guy to the nearest tenth, so we would probably round our answer to the nearest tenth. And what would that be to the nearest tenth? 31.7. So this x value right here would be 31.7. Show me your thumb. Good. That's what I like. All right. Let's go to number 7. You got a negative. Well, let's check it out. Okay, so on number 7, it says the body temperatures of adults are normally distributed. So I've got my normal curve here with a mean of 98.60 and a standard deviation of 0.73. What temperature represents the 90th percentile? So think about this. The 90th percentile means that 10% lies above it and 90% lies below it. Does that make sense? So is that going to be on the right side or the left side? The right side. And what's going to be the area below it? Below it. To the left, and what would be the area of that? 0.9, because it's the 90th percentile. 0.9 lies below it. So they want to know what temperature, this is the x value that I'm trying to find, corresponds or represents the 90th percentile. So we're going to go equal norm dot INV. What am I going to put in for my probability? 0.9. My mean? Good. And my standard deviation? 0.73. And that would be 99.54. If you have a temp of 99.54, you're in the 90th percentile. Okay? That's why, like, it's getting close to, hey, we're getting a fever. We have a low-grade fever here. All right, number 8's a little weird. Number 8 says, ACT scores have a mean of 20.6, and 6% of the scores are above 29. The scores have a distribution that is approximately normal. Find the standard deviation. So here we're going to be working backwards. So we know that we're going to have, it says approximately normal, so I'm going to put my normal curve in there. And it tells me that I have a mean of 20.6. Then it tells me that 6% of the scores are above 29. So it gave me the area and it gave me the x value. So I know that I'm dealing with the number 29 here, okay? And it told me that the area here is 6%, which is 0.06. Now what it wants me to do is find the standard deviation. Find the standard deviation, okay? So what we're going to have to do is start by figuring out the corresponding z value to this x value here. Okay, that's going to sound weird, but we need to figure out what z value, like if my mean was 0, what would this z value be? Okay, and to do that, we're going to have to revert back to my norm.s.inv. Okay? And what I'm going to put in is the probability that falls to the left of it. Now, I know that the probability that's to the right of it is 0.06, so what's to the left of it? 0.94. So since I have an area over here of 0.94, that means the corresponding z value to 29 in this instance is about 1.55. Okay? Then what we're going to have to do is we're going to have to put it into the formula. Remember the formula for z value was x minus mu over my standard deviation. We're trying to solve for my standard deviation. So I'm going to substitute in. I know that my z value is about 1.55, and that equals my x value. What's my x value here that we're working with? 29 minus my my mu, my mean, which is 20.6, and that's divided by the standard deviation. Okay? So we're going to have to work backwards to solve for the standard deviation. Do you guys remember, how do you get the standard deviation by itself when it's in the denominator? What did you have to do? You really just end up, like you multiply by standard deviation, then you divide by about 1.55. So it's really just switching these two. So the formula for my standard deviation here is going to equal 29 minus 20.6 divided by approximately 1.55. Are we okay with that? Now to put that into Excel, we're going to have to use parentheses. So we're going to go equals parentheses 29 minus 20.6. And we're going to divide that, but do you think I want to type in 1.55? No, we're going to do the cell reference so we can get it as exact as possible. And then when we hit enter, we're going to see that we get a standard deviation of about, get out of here, 5.4. I wanted to do that problem because you will have some like that on your homework, and I didn't want you to be blindsided, like, what the heck is this? So make sure you take good notes on this before you start on your homework.